train. Okay, the title is Descriptive Set Theory in Generalized Baire Spaces. Here's the structure of the talk. There are two parts. One is about trees, and the other one is about universally Baire sets in generalized Baire spaces. Okay. Now, every time one talks about generalized Baire space or generalized anything, one should think, my opinion, why generalize at all? Why not be happy with what we have? And does it make sense? Because in mathematics, of course, generality is the rule of the game, but it somehow should make sense. Otherwise, it's bordering possibly abstract nonsense. Now, the classical Baire space has a very strong intuition or motivation behind its real numbers are limits of finite measurements. So everything in natural science and almost any science can use reals. But what about generalized Baire space like omega 1 to omega 1? It's kind of limits of countable measurements. But where is the science or humanities which uses countable measurements? I will argue in this talk, and I have argued for 30 years, that in model theory it has some sense. Anyway, in 1949, Cohen and Goffman, not Paul Cohen, but anyway, Cohen and Goffman wrote a paper, A Theory of Transfinite Convergence, and it seems independently Roman Sikorsky wrote a paper on some topological spaces of high power. They both contemplate on countable limits of countable, in the sense, abstract measurements. And this is really the beginning of generalized Baire space, but it started in pure set theoretic topology with no intuition beyond that, and that indeed is the rule of the game in set theoretic topology, that you consider anything which in some abstract sense makes sense. Now, around the same time came the idea advocated by Mostowski and Kuratowski. That's how I trace it, that one can study countable models of first-order theories or other theories, also second-order theories, by identifying them with elements of the Baire space and then using topological methods, mesotheoretic algebraic methods to get results in logic. In fact, I associate it with kind of Polish tradition in logic to use mathematical methods such as mesotheory, algebra, topology, with no regard to philosophy, whether they are in some sense philosophically not well-founded or whatever. So just any mathematics, as long as you get results. Also Tarski was a little bit in that category. And so here, so in '63, I identify some steps in this process of using topology to study countable models. Scott showed that, answering a question of Kuratowski, that the orbit of a countable model is always Borel. And then using a result of Lopez Escobar, he observed that invariant set in the Baire space is Borel if and only if it is definable in L omega 1 omega. And what Scott used was this very useful tool called Ehrenfeucht-Freitzer game from the 50s, which I will talk about that a little bit, but it makes it possible to use countable ordinals as kind of clocks or measures of the complexity of a countable model or a set of countable models. So we come to this concept of Scott rank. I mentioned two recent results because much of what I talk about in the first part of my talk is otherwise like 30 years old. But of course, there's a tremendous industry behind using Borel, behind the study of Borel equivalence relations. But I mentioned two which are close to my heart and also close in time. The isomorphism of countable models of any complete consistent extension of Peano arithmetic is Borel complete. And the same for CFC with global choice. So this gives for Peano and for CFC for any alpha countable models which are alpha equivalent but not isomorphic. So it shows that it is really difficult to distinguish countable models of these theories from each other. Of course, they are unstable theories, but interestingly, these results have nothing to do with stability theory. They use, of course, they use non-standard models, a technique due to Geifmann and extensions of models. Okay, now in my history of my career, I have been interested in uncountable models rather than countable models. I apologize for this if you like countable models more, but I like uncountable models. I don't know why. Maybe because they are so much more difficult. Okay, and as you will see, like here, let's think of the Erefort game, which is of length omega, as games usually are, interaction of length omega, and the moves are countable sequences. Now here is a complicated uncountable model. You take omega 1 and you replace you fix first a subset of omega 1, and then you replace alpha, which is in A, you replace by 1 plus the rationals, and if alpha is not in A, then just rationals. So you get a linear order, dense linear order like this. If you have another dense linear order, then they look very much very similar. So John Conway showed in his doctoral thesis that, among other things, that these are isomorphic if and only if A and B agree on a club. So if they are discharge stationary sets, then they are not isomorphic, but they are always L infinity omega equivalent, because if you take any if you fix a point, then these parts are isomorphic because they are dense if A doesn't contain 0. They are dense linear, uncountable dense linear orders, and you can continue this by moving this barrier endlessly. So they are L infinity omega 1 equivalent, but not isomorphic. So the natural language for uncountable models, L infinity omega 1, is not going to work here. Now, with Meckler in 1993, we moved from considering countable models as elements of Baire space to considering uncountable models as elements of generalized Baire space. So like models of cardinality Rf1 as elements of this space where neighborhood is by countable initial segments, in the hope that we could use set theoretic and topological methods to understand better the models. There's a problem immediately. that there's a dense set of size continuum, but not all size Aleph1. So a lot of the early researchers, including myself, assume CH in order to have a kind of a balance that you can go through the dense set in omega-1 moves. But CH is not a fact, so in fact, what I'm talking about in this talk is very much a movement, finally, after 30 years, away from CH to situations where continuum is typically Aleph2. But everything in the model theory of these structures is different. More generally, so there is a more general concept of a kappa space introduced already by Cohen and this, what is this early Hoffman, is a kappa space. It doesn't play much role in the rest of the talk, so I will not go through this, but it is just an abstract version of what it means to have this countable information semantics, topology determined by countable initial segments. So it is an abstract version of a space like kappa to a kappa. Okay, so now let's stop for a moment to think what are we after in this generalization from omega to omega, from the classical Baire space to the generalized Baire space. We want to isolate topological properties of uncountable models, which would perhaps explain results in classification theory, like stability theory of Sela, which is typically of uncountable models. Sela plays with this tension that language is countable, but model is uncountable. So there is some tension there. But if language is countable and model is countable, then it's completely different ballgame. So what are the topological properties behind this tension? And in general, how can we say that two uncountable models are very close to being isomorphic without actually being isomorphic? And can we measure such closeness by some method which perhaps is not ordinals? Some history of this. So as I said, this started in general topology. Then there was a period, early 90s, when a lot of papers were written about the basic setup and using trees as generalized ordinals and so forth. I will talk about that. Then later there was another period when there was a lot of results, relatively a lot of results about the structure of trees. And now recently there has been a lot of research. I made here a list, and later I realized what the risk it is to list people, because you forget to mention somebody and then the person doesn't forgive you ever. So I apologize here if I missed someone, but I made a long list because I wanted to emphasize that it seems to attract a lot of interest now. There is a classic result already by Cohen and Kaufman. The Baire category theorem is a kind of the same proof as in the classical Baire space. So the space itself is not kappa Mieke. Here's a result, a Cantor-Bendixson theorem, which already indicates that things become a bit difficult, may become difficult. If we want to generalize the Cantor-Bendixson theorem, which essentially says that the closed set can be split into the perfect part and scattered part, you can do it if you assume a little sidekick, I omega, that there is an ideal on omega 2 such that the positive sets has a dense sigma closed subset, a principle introduced by Lever and proved consistent from a measurable. Then every closed subset of omega 1 to omega 1 is a disjoint union of a omega 1 perfect. And omega 1 scattered parts. But this implies CH. As I said, a lot of the early results were in the context of CH. So now let's go deeper into the topic of EF games and how they are related to this problem of deriving properties of uncountable models from topological and set theoretical principles. So we introduced this natural notion of Erefurt-Freise game of length omega 1. Players play countable sequences, alternating omega 1 moves. And obviously, if the models are actually of size Aleph 1, then they are isomorphic if and only if the second player or isomorphism player has a winning strategy. Because if they are isomorphic, then player 2, the isomorphism player plays the isomorphism. And if they are not isomorphic, then player 1 enumerates the models and he must win because they are not isomorphic. But if we look at models which are not of size Aleph 1, Aleph 2 or Aleph 3, and so on, but we still consider the game Erefurt game of length omega 1, then it's not perhaps so surprising, although it took some time to figure it out, that one has a non-determinacy phenomenon. Especially if V equals L, then one can construct a non-determined. What's that? Yeah, omega, yes, omega 1 squared. In fact, you need non-reflecting set. And if V equals L, then there can be non-determined models of size Aleph 2. But if we assume this principle I star omega, which is like I omega, so but it is a non-stationary ideal. So you collapse measurable to omega 2, and then you kill a lot of stationary sets. Then you get that the non-stationary ideal plus as a dense sigma close subset, and then any two, the Erefurt-Freise game between any two models of size Aleph 2 of length omega 1 is determined, because at the crucial point you can use the sigma closed dense set, and the game is of length Aleph 1, so the sigma closure helps you to get over countable limits. But if the game is still of length omega 1, but the models are of size Aleph 3 or bigger, then there is this gap, and you can use the gap to use club guessing to get always non-determined models. Further results have indicated that this is related to the stability theoretic properties of the first order theory of the model, but I'm not going to go into that. There's a question from the audience.
Is it known if it implies star omega?
Is it known if this implies CH. Okay. Now let's move now from the game of length omega 1 to a more manageable and reasonable game, which is in which every play is countable. And just like in the Erefurt-Freise game of length omega, we have this finite the ranking that that we can rank the game by an ordinal, and the game is always finite. So here we take wide Aronsine tree, or what we call, or Jamonia Selah call wide Aronsine tree, is a tree of size and height Aleph 1 without uncountable branches. So it's different from an Aronsine tree in that levels may be uncountable. We modify the Erefurt-Freise game so that player 1, the non-isomorphism player, has to go up the tree while he plays So there are these two models, and the game goes like this. And then there's a tree. So when player one plays, he has to go up the tree like this. And because this has no uncountable branches, so at some point it ends, so the game is always countable, and it's much easier, or let's say it's just easier for the second player, because she doesn't have to struggle uncountably many moves, but she doesn't know the order type of the moves. So this is harder for the non-isomorphism player because the clock is ticking. I call this a clock. But easier for the isomorphism player. Now, to formulate the result that is coming in a moment, I indicate how to compare two clocks. So if we have a clock, usually called a tree, like this, I say that this is less than or equal if there's a mapping which respects the strict order, but several elements may go to the same. So it doesn't have to be one-to-one. This turns out to be the right order of trees, or the family of all trees. But if this pi is, in a lucky case, one-to-one, then T is simply embeddable into T prime, which is a kind of a more mathematically more natural concept. So this picture indicates why this ordering of trees is very natural for games. Suppose isomorphism player wins with this clock, and we have a smaller clock. Of course, she always also wins for the smaller clock because she just copies the moves into this game. On the other hand, if non-isomorphism player wins with this small clock and we have a bigger clock, of course, he also wins with a bigger clock because he copies the moves from here to here. But finally, if isomorphism player wins with this clock and there's another clock with which non-isomorphism player wins, then one can prove that in fact there's this tree is less than or equal to that and not vice versa, so that this is strictly less than this. So this leads to this kind of possibility of using this tree order to compare how close two models are to being isomorphic. Just to indicate what this is about, let's take an ordinal alpha and then the finite descending sequences from the ordinal. Then this tree order is exactly the same as the ordinary ordinal order. To get a tricky or kind of pathological example, let's take a subset of omega 1 and the tree of increasing closed sequences in this A. Then TA is less than or equal to TB if and only if A is subset of B mod non-stationary ideal. So again, this is like these linear orders phi A, like are typically A is a stationary co-stationary set, and then we get like incomparable trees in this way. But note that these trees are continuum size, so they are not of size RF1. Here is an important operation on trees, by which from any tree you can get to a bigger tree. You take the tree of increasing chains in T. I think John denotes this by T plus in the paper, but it is due to Kurepa from, I don't know, 30s or something, or 40s, and well, I denote it by sigma T. It's strictly bigger tree, again, the size may explode. So if CH is false, then this may be bigger than, but if CH holds and T is a wide Aronson tree, then also this is. So under CH, one can sort of move from a tree to a bigger tree. Of course, in the ordinals, this is just a successor of ordinals. Here is a picture of the structure of trees of size and height Aleph1 under this ordering. There are first there are the well-founded trees, then there are some trivial non-well-founded trees, and then there are the Aronson and wide Aronson trees. As you see from the picture, there are anti-chains also. So this is compared to the case of countable models where everything is well ordered, linear and well ordered. This is a much more complicated. That's why I apologized, because it gets more complicated. But as mathematicians, we also should be not afraid of complications. There is a tough question of whether there is a maximal element here. Intuitively, there shouldn't be a maximal tree, but that's a kind of a tough question. Now here are some questions which were solved early on. Are there for any wide Aronson tree T models of cardinality Aleph1 such that they are non-isomorphic, but the isomorphism player has a winning strategy in this approximated game? And this is a tough question and still open. The answer is yes, if we assume CH, because then one can use kind of canonical constructions using sequences and sets of sequences and so forth. But if you don't have CH, then results are very weak, I would say, although complicated, and Celan has a sequence of papers, but otherwise it's open. An easier question is, if we don't ask that isomorphism player has a winning strategy, but we ask that non-isomorphism player does not have a winning strategy. This is a non-determined game, so it makes sense to ask the easier question. And then the answer is always yes, as proved already in the 90s. So we get this kind of boundary map of the boundary behavior of the advantage in the Ehrenfeucht-Reize game. Here are the trees for which isomorphism player wins. So we have two models, M and N, of size Aleph1. And here are the trees for which isomorphism player has a winning strategy, and here are the trees for which non-isomorphism player has a winning strategy. And there is this action on the boundary that there is a tree, kind of called carp tree here, so that its sigma is already beyond. And here is a tree S, so that the sigma is here, but the tree itself is not there, and they are embeddable into each other like this. So this is an example how you can investigate what has not been so much investigated, although it maybe should be, is if the models are not just arbitrary models, but if they are, for example, in L of R. Now, we can also look at just one model, like in analogy with a Scott rank of a model. A tree is called a universal non-equivalence tree for a single model M of size kappa. If for all other models of size kappa, if the other model is non-isomorphic, then player one has a winning strategy with this clock. Now, a canary tree is a tree which does not have an uncountable branch, but if somebody kills a stationary set, the tree suddenly gets a branch. So it's like a canary which indicates that some stationary was killed. So like there's a poison in the air which kills stationary sets. So this canary tree then, okay. And such a tree exists if and only if it is a universal non-equivalence tree for a free abelian group of cardinality Aleph1. And if we assume again CH, then a model has a universal non-equivalence tree of cardinality Aleph1 if and only if its orbit is delta 1, 1. So this shows that these trees are intimately related to such like topological properties of the models. Generalized Baire space. Okay, it's consistent relative to the consistency of CFC that CH holds and every non-classifiable theory, first order theory, has a model of cardinality Aleph1 without a universal non-equivalence tree. A kind of a cousin of that, because of non-determinacy, there are always these two versions. Here's a universal equivalence tree for a model of cardinality kappa if for all models of cardinality kappa, if player 2 has a winning strategy, then they are isomorphic. So remember, the game may be non-determined, so we cannot reduce this to the previous case. If kappa is omega, then the game is determined, and every countable model has a universal non-equivalence tree of type B alpha plus 1 and a universal equivalence tree of type B alpha, and alpha is the Scott height of the model. Now CH implies that every unstable theory has a model of cardinality Aleph1 without a universal equivalence tree. So again, you see that the stability theoretic properties of the model or the first order theory of the model are related to these classes of trees. Here's a more recent result of the same flavor which identifies the classifiability of a first order theory in terms of the depth of the Borel depth of the or Borelness of the isomorphism relation. So these considerations of the universal trees, equivalence and non-equivalence trees, raise the question of the role of the maximal trees. There cannot be any maximal trees if the sigma operation is in business, because it always gives a bigger one, but sigma operation depends on GCH. Some earlier results on these maximal trees is in my paper with Meckler, we made a false claim that Martin's axiom implies that there is a maximal tree, but it turned out to be false. But the Rotswitz proved that under Martin's axiom, the class of Aronson trees does not have a maximal tree. And Jamoni Sella proved, assuming Martin's axiom, the class of wide Aronson trees does not have a maximal tree. But what is the actual result? So here is the result by Benneria, Omer, Menachem Makirov, and myself. And earlier result of Stevo and myself. So if V equals L and kappa is not weakly compact, for every wide kappa Aronson tree, there's a Suslin tree which cannot be embedded. It is not less than or equal to the tree. So this is like a strong failure of maximality. The more kind of important surprising result is this, that we can force with a weakly compact canal, we can force a maximal kappa plus wide kappa plus Aronson tree. So it means that in this picture, it is consistent to have a maximal tree. And for the non-committed, maybe this is not so surprising, but just imagine if there was a biggest countable ordinal. I think there would be an uproar in the audience. Of course, there cannot be a biggest countable ordinal because you can just add one. But here, if you add one, you may jump into a higher cardinality. So there is no biggest countable ordinal, but there may be a biggest tree of size Rf1 without branches of length Rf1. Okay. So now to the second part, universally Baire sets, which is joint work with Menachem Magidor. And there's independent work with similar but stronger results from strong assumptions by Daisuke Kagame and Matteo Viale, unpublished. Now, typically we do not assume CH or anything like that. Okay, so now I give a definition of kappa universally Baire, which is not unfortunately the same as what Sandra gave, but it is, in the classical case, it is equivalent. So a set A in the generalized Baire space kappa to kappa is universally Baire if there's a uniform reason. Okay, so if for every kappa strategic close forcing there's a term tau, just one single term tau, such that whenever you take a model and a generic, that tau computes the set correctly. So there's a single indicator of what the set is. So which means technically that if we take a big theta and we take an elementary submodel of size kappa, and we take a generic over this model, then the interpretation of the term is the set A that we start with intersected with MG. So a kind of generic absoluteness. But in the case of kappa is omega, this is exactly the same as what Sandra defined. A more familiar formulation is this: A is kappa universally Baire if for every kappa space and every continuous, okay, this is continuous. If F is continuous from a kappa space into this Baire space, F minus 1A is Baire in this set. So this is like the original Feng Magidor-Woodin definition, and like what Sandra, what's that? Oh, Schillingford. Yes, sorry, I always forget that. Yeah. Complaints if you don't mention it. Okay, I have to add it, but I'm not talking about the classical case. So now what kind of properties do these kappa universally Baire sets? The nice thing about universally Baire in general is that they have all the nice properties. You mention it and they have it. Now it's not so here. In fact, it's rather the, okay. So, but anyway, we have the Bernstein property. If A is kappa universally Baire, then either A or its complement contains a copy of 2 kappa. Maybe I say a few words about the proof. It is it's not actually very interesting proof because it is like the proof in the classical case. So maybe I will skip it. But now comes the stumbling block. The club, the elements of omega 1 to omega 1, which or kappa to kappa, which code a club set, that is not even Baire, let alone universally Baire, and it's a sigma 1 set. So obviously we want to go in the direction of sigma 1 sets are universally Baire, projective sets are universally Baire, but we here immediately hit this kind of block. The proof of this, by the way, is not at all difficult. It is like the Baire category theorem, but you just use property that into a club you can, at limits when you extend, you can put elements into the club or away from it. And by the way, if we look at the other important sigma 1 set, the codes of Suslin trees, then diamond implies that that's not Baire. And also the third important set, sigma 1 set 3, the set of elements of the space which code a tree without an uncountable branch. None of these is Baire. Mind you, here we have a CH, so it's not perhaps so important. But because of the club filter, we say that the concept of kappa universally bare seems very restrictive. We want natural objects to be universally bare. And we don't find any interesting sets. So we set back and make a new start. And now let's take a little bit more flexible start. We have an arbitrary set, class P of forcings, a class M of models, and a class G of generics. And we simply say that for every forcing in this class P, there is a term tau which does the computing in every model and every generic. So that for every model which you get from this particular class of models, and for every G in this G, the tau computes the set correctly. I don't think so. Because this is generalized square space, they are all size Aleph1, typically. Countable model here means nothing.
No, okay, but I assume so because in one of the previous slides you said something like it's maybe not kappa or whatever. But then you say G is generic over M, or model M.
Yeah.
But where does G live? Like
V in V. So how do you get this? Okay, so no wonder I'm going to talk about Martin's maximum in a moment in order to find those generics.
So you bring the case of omega.
Yeah, that's the beauty of the classical case is that because you deal with countable models, you always have generics in V. But here we have to, in a moment, talk about Martin's maximum. Okay, so the game here is that we choose the P suitably so that we can, for example, handle the club filter, and we choose the models M somewhat carefully, but we choose the generics even more carefully so that everything works fine. And we are forced into this because we want to include the club filter. So typical forcing notions here is sigma closed and stationary preserving. Typical class of models is internally sigma closed models, so that's not much different from the previous, but for generics we focus on stationary correct generics. Okay, but now let's see how we formulate this in the more familiar terms. So we call a topological space stationary preserving if when we interpret it as a forcing notion, it is stationary preserving. It has a purely topological formulation, which has nothing to do with forcing. And then these are equivalent. The universal bareness with respect to stationary preserving forcings, models which are internally Aleph1 closed, and stationary correct generics is equivalent to for every Aleph1 space X, which is stationary preserving, and continuous F, the preimage has the property of Baire. And of course, for trivial reasons, club filter is now universally bare because we have set up the system so that it is preserved. It can be computed. But if we look at these more tricky sets like the Suslin and 3, if we assume diamond, then they are not UBCC, so not certainly UB stationary preserving. So we have to do something more to include these very natural sigma 1,1 sets. It's not enough to look at stationary preserving. But already now we see that large kernels cannot imply that all analytic subsets in omega 1 to omega 1 are universally bare even in this sense. So I said earlier that the club filter is a stumbling block. It kills the pleasure of just going in the classical lines. We have to go to stationary preserving, but now the Suslinity and treeness, which is very important, are new stumbling blocks. So we have to go further, and I have to introduce further restrictions. So we introduce these concepts: stationary preserving MM, which means stationary preserving, and MM inducing, which means that the force is MM, and stationary preserving and star inducing, so the star is forced. This may seem like a big major league cheating, but that's the only way we can go forward in this. What's that? That it forces star, a wooden star. Of course, if you have a proper class of supercompact canals, you can always get this kind of forcings. Okay, so here's the first result. There are two results. The first result is that if we assume a proper class of Wooden canals, then every sigma 1 subset here is universally bare in this sense that if you have a forcing which stationary preserving and induces Matisse maximum, and you have stationary correct generic, then you can have universal bareness. This uses stationary tower forcing, but I will a very important little fact here which we use is that if you have a sigma 1 property of an element of omega 1 to omega 1, and it can be forced with a stationary preserving forcing, and Matisse maximum is true, then it is already true. So we can, if we assume MM, and we have MM in the generic extension there, we can sort of arrange things in a forcing extension, and because we are dealing with a sigma 1. Okay, so another result. Now we assume star and a proper class of Wooden canals. Then every projective subset of omega 1 is UP, universally bare, with respect to stationary preserving and star inducing forcings. The trick. Star. Instead of proper class of Wooden canals, we can use this. So the trick here is that we reduce the question using star in both M and MG. We reduce it to a question about reals, and then with our assumptions, R sharp, the sharp of R exists and is universally bare. So we have this hiccup here that we have to eliminate a dependence on a generic for this arbitrary forcing P, which is here. But we can subsume this G because we reduce everything to R sharp, and R sharp is sort of the same in M and MG because of its universal bareness. Then, this is the final result. What can we do with this somewhat artificial looking concept, universally bare? Do these sets have some properties that we would like to have? As I said earlier, the universally bare sets in classical bare space have every nice property. Does this have any nice properties is the question now. Well, at least if you have a set there, then either the set or its complement contains what we call a rake, and a rake is something like this. So there's a stem like this, then there is a full binary tree, and then these are isolated. So you see already here we have size Aleph2. So if we have a the point of containing 2 to Aleph1, which we cannot do here, is that a big set should contain like a perfect subset, like a canonical subset. We cannot prove that for some reason, which is something related to generic correctness, but we can get this kind of canonical subset of this set or its complement. So it's better than nothing. Okay, now bottom line, the club filter is a stumbling block in generalized descriptive set theory, at least universal Bairness, generalized Baire spaces. We can overcome this club problem by restricting to stationary preserving forces and stationary correct generics. UB sets can be meaningfully defined even if they are not even Baire. So like club is not Baire, whatever we do, it's not Baire, but it's universally Baire. It's a bit paradoxical, but that's how it happens. And they obey Bernstein-like properties. What is a little bit unclear to us is how ubiquitous is this universal Bairness in generalized Baire spaces. We saw under the certain assumptions that our concepts cover sigma 1 and projective, so it's kind of quite a lot, but the concept is rather narrow. Does our universal Bairness help us understand uncountable models is future research. Thank you. Yeah. No. Yeah. So when we try to construct a perfect set, we construct a tree of a perfect tree, and then we have to extend these branches. But then when we come to omega 1, we have a sequence of generics which are generically correct, but there's no way to argue that the union is generically correct. While if we deal with the previous concept of kappa universally Baire, where we do get a perfect subset, the generic didn't have any restrictions, just any generic. If you take an increasing union of generics over models which increase, then the union is generic because every dense set is in one of the models. But if you insist that they have to be generically correct, you can't go over the limit. You can't go through the union. It's not anymore generically correct. So if you can show us how to make increasing union of generically correct generics so that the union is generically correct, then we can get the perfect subset. Where the hypothesis that I wouldn't call it to get that R sharp is universally Baire. Yeah. So if you just assume R sharp is okay, that's another possibility. Yeah. But I use elsewhere. Elsewhere there are. Yes, it's all over the place. For example, here. Here, oh, sorry. Here. Okay, so here, for example, we iterate a stationary tower, forcing to get the model on.
Why do you need a measurable above?
You take an elementary submodel of the universe which has a measurable.
Consistent with
It's I think it's a famous open problem.
it's open.
Yes, it's open. Yes.
Yeah, it implies MS is omega 2 saturated.
Okay, so let's thank the speaker again.
One very short announcement. Sorry for